You train a model, you split off a test set, and you got a great score. But how much do you actually trust that one number? Because that single split could have been lucky or unlucky, and you would honestly never know the difference from a single result. Maybe the easy examples happen to land in your test set. Maybe the hard ones did. Today we're looking at cross-validation, the technique that turns one shaky, fragile estimate into a stable one by rotating which slice of the data you hold out. Let's walk through exactly how it works and why it matters so much. Now, the heart of this is a loop called k-fold. Follow the data around it once, and the whole idea clicks into place. Start by chopping your data set into equal pieces called folds. Maybe 5 of them, maybe 10. Each fold is just a chunk of your rows, and together they cover the entire data set with no overlap. Then you set one fold aside as the validation set and train the model on all the others combined. The model never once sees that held-out fold while it learns, so scoring on it afterward is a genuinely honest little test of how it handles unseen data. After training, you record how the model does on that one fold you kept back. That gives you a single score for this round, but here's the whole trick. You're not going to stop at just one. One score is exactly the fragile number we started out trying to fix. Instead, you rotate through every fold. Each one gets its turn as the validation set while the rest do the training. And once you've been all the way around the circle, you average those scores together into one reliable, trustworthy number. So why go to all that trouble instead of one clean split? Put them side by side, and the difference is obvious. With a single train test split, your whole verdict rides on the luck of that one draw. Land an easy test set, and you look brilliant. Land a hard one, and you look terrible. And either way, you've thrown away perfectly good data you could have trained on. It's a noisy measurement dressed up as a confident one. This approach spreads the risk around. Because every point takes a turn being validated, no single unlucky split can fool you, and averaging the folds gives you both a steadier estimate and a real sense of how much it wobbles. All right, let's boil this down to the 3 ideas that really carry the weight. First, you train the model several times over, each round holding out a different fold as the validation set. Yes, that costs you more compute than a single fit, but what you buy in return is real confidence that the score isn't just a lucky fluke of one split. Second, every single data point gets validated exactly once across the different rounds. Nothing is wasted, and your estimate leans on the whole data set rather than one arbitrary slice of it. Third, the payoff is a stable, lower variance estimate of true performance, plus a sense of how much that performance actually varies. That's exactly what you want for comparing models fairly and for tuning settings, all while you keep a final, untouched test set locked away for the very last check. Okay, let's lock in the essentials before you go. The technique rotates which fold is held out, training the model several times, and averaging the scores into one dependable number. It beats a single split because no one lucky or unlucky draw can quietly mislead you about how good your model really is. Handy variants adapt the loop to your data. Stratified folds keep class balance for imbalanced problems. Leave one out goes fully exhaustive, and time series folds never let you train on the future. Mainly you'll reach for it to evaluate models and to tune settings on solid ground. And the only real cost is training several times over. If breaking down machine learning concepts like this is your thing, Standarity.com has a whole library of explainers waiting for you.